My name is Martin Paterson. I'm the Chief Commercial Officer of C2CA, and unfortunately today I'm not able to participate live, so we had to record this session in advance. I will share the presentation, and while I'm sharing, let me say that I feel really happy and honored to being invited, talking in front of such a diverse and selected audience. So thanks to Theo and the team for giving us the stage. C2CA stands for Concrete to Cement and Aggregates, and our vision is to phase out the use of virgin materials in new concrete, also to phase out the use of cement in new concrete, and thereby reduce global CO2 emissions by 2%. Today I will explain you a little bit about the challenge in the industry, the challenge of the cement and concrete industry. I guess most of you know a lot about it, but it's always good to put some numbers, but also show the opportunities, so the positive aspects, the levers we have in order to face these challenges. I will explain more about our technology, the process, and the products we are producing, and then I will close up with some commercial indications of our business. So let's look at the figures briefly. Annual cement production at the moment is 4.1 billion tons globally, which is equivalent to a CO2 footprint of 2.6 billion tons, 8% of the total global greenhouse gases. And I think the industry has clearly understood that we have a big lever here to reduce and match the targets of the 1.5% of the 1.5 degree warming. A lot of the improvements in the industry have already been started. I mean, the industry is working since many years on improving efficiency of the plants, on implementing alternative fuels. For me, the biggest lever, one of the biggest levers, is the reduction of the clinker factor, and the clinker factor currently globally is at around 70%. Actually, it was lower already, but it increased again. And the reason for that is scarcity of the current additives, mainly being slag and fly ash. But even with a clinker factor of 70%, we already need 1.2 billion tons of additives in cement today. And if you look at other scenarios moving forward, like the VDZ scenario, for example, which assumes 35% clinker factor, 2050 onwards, the demand for additives will be almost tripling. So to summarize the challenge, we actually need more cement in the future. We need to build a city of the size of New York every day until 2050. We almost have a tripling of additives demand, and the current additives or supplementary cementitious materials are getting scarce. Soon there will be no more fly ash. Also slag will be disappearing due to new production methods for steel. So we need new alternatives, and this is obvious. This is not a presentation about SCMs in general. I think that will be a different topic, and I'm sure a lot of you guys are working on some of those. But I wanted to show the overview here in order to make clear that there's many alternatives, and I think all of them need to be explored and elaborated and see whether it makes sense. What is their quality? What is their availability? How do the logistics look like? So closing this gap, this 3.3 billion tons of additives, which will be needed in the future, is not an easy task, and there's no no competition between these different SCMs. All of them have to work. You can see that below the emerging column, we have construction demolition waste and concrete recycling fines, and this is where we'll focus on today. So let's look at the positive aspects. There's a lot of feedstock available when it comes to concrete waste, 3 billion tons annually globally. And this is not considering all the landfills which have been made over the past decades. So the feedstock is massive. And on top of the 3 billion, we also have concrete returns, which is calculated to be approximately 500 million tons annually on top. And the positive aspects of this is that 15 to 30% of this feedstock is cementitious, of course, depending on the application of the previous life of the waste concrete. So if you make a rough calculation, we're talking about a feedstock of roughly 1 billion tons cementitious material, which is at the moment being either landfilled or downcycled. Very few applications where it's been upcycled or used as a filler in concrete. Another big advantage of concrete waste or the cementitious content in that is that it's available close to the point of use. Concrete waste is being produced in the big cities, and that's also where you need it afterwards. So one of the big problem of many other SCMs you saw on the previous slide, that they need high logistical efforts, is not the case for waste concrete. You also produce gravel and sand. Okay, I'm writing here as a side stream, which is maybe not fair, but our focus in the process is really to generate out of the waste concrete a high yield of clean, of high quality cementitious paste. But of course, at the same time, when we do this, we create very clean gravel, very clean sand, which can also then directly be returned into the concrete and serve the construction industry. And basically, if you do it right, there's no waste streams out of this process. It's 100% recycling rate. So fully circular. What are we doing in C2CA again? In a nutshell, we have waste concrete, we put it into our process. Out of that, we get 3 main material streams: aggregates, sand, and a cementitious paste. And if you look at the later one, the cementitious paste, after it's being activated in our process, and I will show you in a while how this looks like, we have a third-party verified carbon footprint of only 11 kilogram CO2 per ton of product. If you compare that with the primary production of cement, okay, we're stating 900 here. Some or many cement plants are meanwhile better. I explained already at the beginning that efficiency has been improved in many plants, thanks to God. But even if a modern cement plant can produce cement with 650 kilograms CO2, it's 50 times less. The process, and let me get out a pointer here. So what we do is we receive end-of-life concrete here. We're not doing the demolition or anything. This is done by partners. So we receive the end-of-life concrete at site. We do a 2-stage crushing. First stage to just simply downsize the bigger concrete elements. The second phase more to rub off the cementitious paste from the stones. So it's no impact crushing, it's more attrition what we're doing here. And we have developed a special process for that. And we get 0 to 16 millimeter out of this 2-stage crushing. Then we go into our first own patented technology, which is the ballistic separator, where we get 3 different material streams out of it. The first one, and that's why it's gray, is the so-called recycled coarse aggregates. That's comparable with a natural gravel, and we take it out of the process here. If we find out in the process that this coarse aggregate is not clean enough, then we can recirculate it and run it through the second stage crushing one more time. But normally we see that this is already a very good product with a low water absorption. The other two products coming out is a intermediate 1 to 4 millimeter and a smaller 1 millimeter. I will come to the later afterwards. The 1 to 4 millimeter goes into the third process step, which is the thermomechanical separation, where we basically have sandstones still having a lot of cementitious paste around it, and we shock heat them, and then the stone expands and cracks off the cement paste. So we get another two material streams out of that. Recycled fine aggregates, which is now a very dry and clean sand, and the ultrafines. And the ultrafines and the fines out of the ballistic separator this is our feedstock material now to produce our SCM. Many companies, I think, are doing some kind of recycling nowadays of waste concrete. They do it in a dry process, semi-dry process. Some do it with chemicals. And up to here, I think the performance might be better or lower, but it's not too different. What is really different is that we take this fines and we now activate it. And the activation, I will also show a detailed slide later how it works. But in principle, we downsize the fines further. We grind them down to a D50 of 10 microns. After the downsizing, we separate one more time the silica particles, since we cannot activate them, and then we have a more clean material. And further, we take the flue gas coming out of the thermomechanical separation to activate it. So we get what we call a fine inert filler. That's the silica particles we separate, and we get our recycled cement paste, which is highly reactive and can be used either as a replacement of cement and cement mixes, or as a direct replacement of cement and concrete. It's not only a theoretical process. Machines are available and they have been tested with several thousand tons of material, and they are in commercial scale already. So the machines you see here are the same size of machines we're going to use in our first commercial lecture plant now, which I will show later in the presentation. All of them are patented. So we have two patents for the machine. We have an exclusive license to use the ballistic separator for concrete waste. And we have filed two additional patents in March this year, and one of it being for the entire process I just explained. Of course, we're doing further innovation. We have 3 additional patents under preparation. A lot of it is, of course, on the quality control and tracing, since waste concrete is not equal to waste concrete, depending on where you are in the world, and depending on the application of the old concrete, there can be pretty high fluctuations. And of course, a lot of our innovation, a lot of our IP is in that field, in order to homogenize, in order to adapt the process based on the feedstock material. And there's more to come here. As I said, the activation of concrete fines, a little bit more detailed. So first of all, we downsize it. Here it's mentioned 15 microns, but we rather go smaller. We also remove the quartz particles after the grinding. Then we carbonate it in a semi-dry process. The carbonation time depends of course, heavily on the moisture of the material, but since it's almost dry, we need quite some time to do it. And the thermal treatment, since we're also applying heat, low heat, I mean, it doesn't really it doesn't really affect the reactivity of the material, but it accelerates the process, and it increases the ability of CO2 being captured. So I already talked about our first commercial scale plant. This is how it will look like. The engineering is done. And on the last slide, I will give you more details about the project, but you can find some of the machines we just saw on the pictures. So this is the ballistic separator. Here you start with a two-stage crushing process. You go into the ballistic separator, you take out the RCA, you go to the thermomechanical separator, 2 units here. You take out the RFA, and then the fines are collected here. You feed them into a mill. It's a ball mill, which you see here in the back. After the mill, it goes to the carbonation tower, and from the carbonation tower into the storage silos. So where are we right now as a company? We were founded in 2016, so we did a lot of analytics, a lot of testing on the materials, investigated the material properties together with academic partners, industrial partners, with certification bodies. So the database is huge, and we know quite a lot on how our material reacts, not only as a material property, but also within concrete. So also there we have done quite a lot of testings. We were also in the happy situation to be part of a governmental project in the Netherlands called the Climate Envelope, where we did 6 real-world constructions, and now these constructions are being permanently measured and watched by SGS. So we can also have meanwhile long-term durability data available, and we know how it reacts in real-world applications. We have launched quite a lot of partnerships. One is our first commercial scale plant, where we implemented a joint venture with one of the big Dutch construction companies, Dura-Famea. We also already signed a lot of intentional offtake agreements and intake agreements, since the plant will be operational soon, but more to come afterwards. And what is good is that we're ready to scale this globally. So we have now defined the full process. It's engineered, and the business model allows us to accelerate this globally now and to start the rollout. A little bit more in detail about the product. So you see the ternary phase diagram here. Since our material is semi-hydraulic and semi-pozzolanic, it's located somewhere in the middle, and that's how it looks like as a powder and within a concrete block, where we used 50% of that material. We have also tested a lot on the reactivity. You can see here, down here, that we are almost within the range after the R3 test, within the range of fly ash already. But please keep in mind that this material produced so far was done without a comprehensive crushing and without the dynamic activation. So we are very sure that we can move this bar up the ladder and get closer to the SCM potential of slag afterwards. And the good properties have also been shown in the strength activity test. So you can see here the limits which are needed for fly ash replacement and for slag replacement, and our material has been well above that. So it's suitable to be a good SCM, and that's proven. Also, the legislation is partially in place, at least in Europe, and meanwhile in parts of the US. If you want to replace cement within a binder with recycled concrete fines, so lucky-wise, the EN 197-6 has been established last year, and it allows up to 35% replacement of cement with recycled concrete fines. If you want to use our recycled concrete fines directly in concrete, it depends really where you are. Concrete is a very regional business, as you know, and also the legislation is very regional. What we're doing right now in the Netherlands is that we are applying for a specific recommendation by the government, which is based on the EN 206. And they are currently now setting up a working group. 1 year later, we will have a recommendation which will then allow us also to get our recycled concrete fines certified as a reactive binder directly into concrete. And I'm sure that after this process, we will also have a good blueprint for other parts of the world to get the same certification process started. Quality control is mandatory, and the quality parameters interesting for us is the yield of the reactive or of the let's say amorphous material which we can make reactive afterwards. So we currently measure and test how much of the recycled cement paste we can get out of the waste concrete. We need to measure and react on the amount of quartz within the material, as this cannot be activated afterwards. The particle size distribution is very important. And then finally, after the carbonation has been conducted, we need to measure the degree of carbonation. So we have a defined quality control life cycle. We first of all check what comes in. The raw material we get, we already try to source high quality raw material in order to have the highest potential, and we can do this. Then we homogenize the feedstock material. If we see that that there's high fluctuations in incoming feedstock, we can homogenize already before going into the process. Then we have a permanent measurement of the quality within the process. We can adjust the process parameters in each and every step of our process. And finally, we can test what comes out and can easily adjust the carbonation conditions in order to improve. And if that doesn't work, if there's still too much fluctuations afterwards, we can still blend different qualities in order to make sure that we get a stable quality which can be sold to our customers then afterwards. A couple of slides on the commercial rollout before I end. The market is massive. I showed you already at the beginning, and there's nobody at the moment in the world is doing upcycling, and we see a potential long term for 6,000 to 15,000 plants globally. The addressable market is roughly 100 billion euro by 2050. And as we said before, it's urban mining. So there's that's the good thing about the commercial rollout. Since we don't need any logistics, we can produce this material from local demolition projects and consume it within the same region, let's say an area of 20 or 50 kilometers, to be used afterwards. Our commercial rollout strategy, go-to-market strategy, is separated in two phases. Phase one we're looking at now. We want to be the operator of the plants. We want to demonstrate, first of all, in the Netherlands with our first flagship, that the process works and that we can deliver this steady output of high quality materials afterwards. So we will build, own, and operate the plant in order to mitigate the technology risks, but also demonstrate the assumption of the economic model. So we have been building up this economic model for different parts of the world, and we need to make sure that it works and that it's viable. And finally, of course, we also want to showcase our process and conduct further R&D. In the second phase, we will build 8 further flagship plants throughout in different strategic locations in the world. This phase will take, let's say, another three years, and we will follow the same build, own, operate model with strong local joint venture partners. Since we cannot establish a new brand and get new license, so these partners out there, they need to have already operations ongoing. And once we have these 8 plants up and running, and we have proven the concept technically and commercially, we will shift to a more service franchise model, where any construction company in the world, any concrete manufacturer in the world, or recycling company can come to us and say, "Hey, your business model fits. We wanna apply it to ours," and then we deliver the plant and we support with the training. We also can support with the certification, with the ready mix designs, and then we service our partners globally. Just to show you some numbers, which mainly depend on the Netherlands, but also are compared with the US. So on the left side, you can see the revenue. Out of 1 ton end-of-life concrete, we can generate approximately 30 euros in revenue. Most of it comes from the cementitious binder, of course, as it has the highest value, but also the coarse aggregates play an essential role. And then another thing which is shown here in the graph is that we of course have an economy of scale, meaning the bigger the plant, the higher the EBITDA. But we have decided to only build 2 standard-sized plants, 200,000 tons per year and 500,000 tons per year, since we wanna, as mentioned before, we wanna operate in regional businesses. We don't want to build mega plants with high logistic efforts. That will kill the business case, and it will also kill the sustainability aspects of the business. So we have these 2 plants. Of course, the more you can source in that regional environment, the better the business case looks. And since the costs are pretty high in Europe and specifically in the Netherlands, mainly energy, mainly manpower, the business case looks better if you go to other parts of the world. For example, in the US, where energy costs are still lower and also the revenues are lower since there's higher cement prices. Final slide. I mentioned it already a couple of times. We have created our first joint venture company in the Netherlands together with Dura, where we are owing half of the company and Dura is owing half of the company. This photo, which you see on the right side, is an existing location from Dura Urban Miner in the south of Rotterdam, where they have started a couple of years back already to recycle waste concrete and use it for road-based aggregates. And now we're going to build our plant here in order to really upcycle and create high value product. This plant will be the bigger one, the 500,000 tons per year, but we will only process 150,000 tons per year at the beginning due to the existing operating license. But yeah, most probably this will change over the years and we can amend the license moving forward. It's at the waterfront. It's very close to the port of Rotterdam, which will of course give us the opportunity to receive waste materials by water and also send out the upcycled materials afterwards. And the start of operation is scheduled for Q2 2025. So I guess that's it. Again, sorry for not being here live, but please address all your remarks, questions to Theo. And please get in touch, reach out if you want to know more, and if you see potential in collaborating with us. Thanks a lot. Have a great day. Bye.